Okay, hello, good afternoon. Um, some announcements. I have posted the equation sheet for exam 2. You can go and download it and look at it. It's going to be, if you haven't looked at it already, might seem shockingly short. There's probably 6 equations that are going to be important for this exam, maybe. That's it, a few constants. That's really it. So I probably could have just included them on the exam itself. I will, but now you have a copy of them also. It is a couple of equations from statics, a couple of equations from fluids and motion. That's it. And the two homework sets. Kappa, where we at? 7 is due this week. On Thursday evening. Exam 2 is Friday in class. If you are planning to not be here on Friday to take the exam, I need to know fairly quickly so I can make the arrangements and plan ahead. If I have not already heard from you, please, and you are not planning to be here, please let me know as soon as you can. Hopefully, preferably today. Questions about any of that? Okay. There were several. I had a whole bunch of slides left set for yesterday. Oh, was it Monday? No, Friday. Today's Monday. And I just didn't show them for some reason. So let me show them now. These are mostly pictures, diagrams from your textbook. This is a graphical representation of the zeroth law of thermodynamics. In other words, if you take a thermometer or anything else and set it into thermal contact with object A, and that how do we know that a thermometer is in thermal equilibrium with something? What do you mean by thermal equilibrium? We sort of threw that term out, and I think I defined it, but you may not remember what we were talking about. Let's start there. What is thermal equilibrium? That's right. It means that you have these two things in contact. Energy could flow from one to the other or from the other to the one, and energy always does flow between them, but on a net, exactly the same amount of energy is flowing in one direction as in the other direction. That's what thermal equilibrium means. And you can tell that a thermometer is in thermal equilibrium with something. How? What would happen to the reading of a thermometer if it were not in thermal equilibrium? It would change. The number would change. It would actually look like it was changing in temperature. Great. So it's got some reading on it, our thermometer of A. You put it in the other isolated container in B, and it reads the same number. You put all 3 of them into contact with another, and there's no net energy exchange between any of them. That's what we mean by thermal equilibrium. That's what we mean by temperature. It's a quantifiable, measurable number. It means something. If this wasn't true, none of the rest of the stuff that follows would be possible. Okay. What else are we talking about? Oh, yeah. So then we went off to talk about temperature scales, and we got into this point for the definition. So we talked about Fahrenheit, and it's a two-point scale. Talked about Celsius. It's a different 2 points, but it's also a 2-point scale. And now we're talking about Kelvin, which is the most logical and well, that's not true. We're going to use Celsius moving forward also, but only for delta T's. For actual T's, Kelvin is the only logical thing to use because the 0 point really is 0. If you double the temperature of something in Kelvin, you really have doubled its temperature in some quantifiable way. And that's not true with the other 2 scales. So we have, at the very end of class on Friday, we talked about what the scale is. So it's a scale that's set up to have the same delta T's as the Celsius scale. In other words, there's a full 100 Kelvin difference between the boiling and the freezing point of water, except that 0 is at absolute 0, and that sets the scale. The formal definition these days is that the Kelvin scale is defined to be that temperature scale for which the triple point of water is 273.16 Kelvin. Now, what do I mean by the triple point of water? I mean, there is a temperature at which liquid water and solid water and gaseous water can all coexist at the same, in the same area, in the same volume, thermally insulated, in thermal equilibrium. So no net exchange of energy is happening between the gas phase and the water phase and the ice phase. Here is a cartoon showing such a thing. You've got a contained vial, glass container. It has both water ice and liquid water and water vapor in it at the same temperature, and nothing's freezing or melting or condensing or sublimating. It is in thermal equilibrium. How is this possible? There's 100 Kelvin difference between the boiling and the freezing point of water. It shouldn't be that gaseous and solid water can be in thermal equilibrium with one another. How is this possible? What is it? This is a thing. Why is it a thing?
Is it because of pressure?
You're on the right track, Isaac. I got a Zoom answer that is a one-word answer that I basically answers the same question. So let me say that one-word answer. Which was that, Zoe? The answer is pressure. At atmospheric pressure, it is true that there is a 100 Kelvin difference between the boiling and the freezing point of water. But the boiling and freezing point of waters is not 100 Kelvin apart at other pressures. And it turns out if you change the pressure a lot, the boiling and freezing points of water come closer and closer and closer together. And there comes a point at which they meet, they merge. There is a specific pressure which is nowhere near atmospheric. Oh, it's on the next slide. It is much, much lower than atmospheric, whereby these three can exist at the same point. A single pressure and single temperature at which that happens. So again, this is one atmospheric pressure, the Earth, right? So there is 100 Kelvin difference between this green line and this green line at this particular pressure. But if you raise the pressure or lower the pressure, the freezing point doesn't change all that much. In fact, this is a much condensed graph. There's actually far less movement here than it looks like there is. Almost all of this happens in the boiling point. And as you increase the pressure, the boiling point gets higher. If you decrease the pressure, the boiling point gets lower and lower and lower and lower. The temperature gets lower and lower and lower. And finally there comes a point at which, these three can exist in the same place at the same time at a specific very low pressure. That's the triple point. So has a well-defined pressure and a well-defined temperature. We can well-define that temperature. You can do this in your lab. You can do the experiment and say, okay, I can calibrate my thermometer because I know that the Kelvin scale has to be this specific thing, 273.16, at this particular temperature where these three things exist in thermal equilibrium. By the way, here's the atmospheric pressure on Mars. It's below the triple point pressure, which is a little more than 1/100th of the atmospheric pressure. What does this mean? Well, it means that there is no real liquid phase for water on the surface of Mars. It cannot be that there are liquid rivers and lakes today on Mars on the surface, because if you're too cold, you go straight to frost, and if you're too hot, you go straight to vapor. There is no liquid phase anymore. You go straight from solid to vapor, and from vapor back to solid. We think far in Mars's past, there was a more substantial atmosphere, and that far in Mars's past, the atmospheric pressure was higher, and far in Mars's past, billions of years, there probably was liquid water on the surface, but you have to have the pressure above a certain threshold to even have a stable liquid phase for water at all. And most substances, as you say, Isaac, have a diagram that looks on the, I assume this is what you were talking about. Yep. So, yeah, so this is pressure on the y-axis and temperature on the x-axis. Okay, close that out. Okay. So just some warnings. Again, you're not going to have a kappa set until next week on this. But when you do, there's some things you're going to want to know and remember. And you can look back in your notes to remember them. Whoa, what am I doing? Here we go. There we go. For kappa, what units are you going to use? You can use deg C is degrees Celsius. And that is a specific temperature. If you plug in deg C or deg F, it will know what you mean, and it will mean a temperature. Believe it or not, it cannot translate between deg C and Kelvin. So if it asks, I'll be pretty specific. Whenever you want a specific temperature, you should not use deg C really. You should probably use Kelvin, because this cannot go to Kelvin or back, or vice versa. Just because there's not a fundamental difference. You can go back and forth between them, but the formulas don't work all that well for deg C. So kappa has a hard time with it. That's for absolute temperature. Delta T, if you have a change in temperature, this is for temperature. For change in temperature is different. A delta K equals a delta C. But there is a different unit for a change in temperature in Celsius as there is for an absolute number in Celsius, because they are fundamentally different things. And so there is another thing called CDEG, which is the kappa equivalent of Celsius for a change in temperature. This is confusing. 1 meter, a delta, if you have a length scale, 1 meter is 1 meter, whether it's an absolute length or a change in length. That is not the case for the Celsius scale. A delta C of 10 degrees Celsius is way different than an absolute number of 10 degrees Celsius. Those are two fundamentally different things. So just know that it can go, so whenever you put in Kelvin, it's thinking about the absolute, it's not thinking about thinking about the relative. So it can't, if you put in a K, it won't know which one you're talking about. So it will think you're trying to get to a delta C, which is really why it can't do both of them. It can't have both of those definitions in there. It has to be one or the other. Kappa is choosing the delta because they're actually equivalent. The change in temperature of a particular number in delta K is exactly the same as the number. There's no reason really to use CDEG, because K will work every time because they're exactly the same. So just be aware of these weirdnesses. If you do want to use a temperature in degrees Celsius, use the deg C, an absolute temperature. If you do want to do a change in temperature, you can use either one, but they're equivalent. Okay. So Kelvin is easier, and if you can, stick with Kelvin. Okay, good. Thermal expansion. In general, as you heat an object, it gets larger, with very few exceptions. How much larger does it get? We're going to think about this in two ways. In one dimension, delta L, in other words, it's a change in the length of something, is equal to the length of that thing times alpha times the change in the temperature. Where alpha, we're going to define to be the coefficient of linear expansion. In 3D, we've got the same exact equation, except we're now talking about changes in volumes rather than changes in length. Delta V for volume equals the volume times beta times delta T, where beta, you can probably guess, is the coefficient of volume expansion. Okay, let's think about these equations. You have a steel rod or a copper rod or a rod of any length at all, or any substance at all. You heat that object, it gets a little bit longer. How much longer does it get? The longer it is to start with, the longer, the more it will grow, right? A 10-centimeter rod will grow twice as much, will go half as much as a 20-centimeter rod. That sort of makes sense. And obviously it's going to be related linearly to delta T. So if you change the delta T is 10 degrees or 10 Kelvin, it will have half the expansion as if you change the temperature 20 Kelvin. And alpha and beta is substance dependent, material dependent, will set how much that expansion actually goes. Pretty straightforward, but it gets confusing fast, as you'll see in the homework. What are the units? We defined two new terms, alpha and beta. What are the units of alpha? Inverse of the temperature. That's right. We've got length on both sides. They cancel out. All we have is an extra temperature on the right-hand side. Alpha better have an inverse temperature, units of inverse temperature. So let's say 1 over K or 1 over degrees Celsius. This is a capital K for Kelvin. What are the units of beta? They're exactly the same. This time we have a volume on both sides, and beta is going to have exactly the same units, 1 over K. Okay, now, this gets a little bit confusing, and so let's unpack this a little bit. What do we mean by L? We have some rod, we heat it up, it gets bigger. Is L the beginning length of the rod? Is L the ending length of the rod? Is L some halfway in between value? Sorry, ask that question again. Do we that's a good idea. So the comment was, do we have to think about how changing the atmosphere will change the pressure and things other around it as well? Right, right. So Isaac's comment was, we should be able to, whatever L we choose, we should be able to start at a value, change the temperature to some other value, start at that new value, go back to that original value, and get back where we started from. So whatever L gives us that should be the L we use. Is that, am I characterizing what you said okay? I'm really asking what conceptually is L? Since we're changing the length of the rod, is it the length at the beginning? Is it the length at the end? We're changing the temperature and that changes the rod, but I only have the length of the rod in there and we don't have any specific actual length of the rod. Would it be just the initial length? Let's try it out. Let's do the experiment that maybe you weren't suggesting, but that I put in your mouth that you were suggesting, and take your suggestion for what the actual L is. Let's set it at the beginning L. Let's increase the temperature. We'll increase the length of the rod, and then we'll do the process in reverse. We'll take that L to be the initial length of the rod. We'll move it back down and see if we get to the original point we started with. What is L? And this is really equivalent to asking what is V, because I could do exactly the same thing with a V instead of an L, and we're going to get to the same question. So let's try the suggestion that L is L initial. And let's do the experiment. Let's increase the temperature. Let's heat it. What's it going to look like? Delta L, we know, equals L2 minus L1. This is the length of the rod at its end point minus the length of the rod at the beginning point. Again, if delta T is positive, L2 minus L1 will be positive, because L1 is where we started from, and L2 is where we are going to. So that's L2 minus L1 is equal to, again, we're going to choose L to be L1. That's this assumption, times alpha times delta T. So let's solve for L2. L2 equals L1 plus L1 alpha delta T. Or I can pull the L1 out. This is 1 plus alpha delta T. Okay, great, fine. We have some new length that is bigger than the other one, right? We've taken the old length and we multiplied it by some number. Alpha is generally small, so a little bit larger than it was before. This works fine. Great. Now let's cool it back to its original point. Again, we're starting this problem again. My initial length now is my longer length, and we're going to cool it back to the original point. Let's see what happens. Delta L now equals, let's say delta L, sorry, not delta, equals the final length, L minus the L2 length, right? So that's, again, we're starting at L2, and we're going back to, we're going to cool it by the same delta T and see where we get. Let's see what LF is. This is going to be equal to L2, because that's our starting point, times alpha delta T. We'll call it T2, but we know that delta T2 is equal to negative delta T, because we're just cooling it back down by the same amount we started from. So what does this look like? This is negative L2 alpha delta T. Plugging this in. Okay, so let's solve this for LF. LF equals, we've got L2 minus L2 alpha delta T. And we know that L2, this is L2 times 1 minus alpha delta t. Well, we know what L2 is. L2 is just L1 times 1 plus alpha delta t. Let's plug that in. Equals L1 times 1 plus alpha delta t times 1 minus alpha delta t. That's the final length. Okay, well, I can, this is L1. I can merge those two. This is actually 1 plus 1 minus alpha delta t squared, right? No, it's quantity squared. No, that's not right. Uh-oh. Math is escaping me all of a sudden. That is right. Yeah, I had it right. That is right. Yeah, that's right. I was right the first time. Good. Got worried there for a second. Okay, great. That is not equal to, no matter how it comes out, does not equal to L1. And yet we know that if we take a rod and we heat it up, we change its temperature by a certain amount, and we change it back, we have to get back to the original spot, right? That's how physics works. This does not work that way. So L1, L cannot be the initial. Turns out it can't be the final either. Turns out this doesn't really work for any specific value of L. So what is happening here? This is really only a linear approximation to something more complicated that's going on. That's really the bottom line. This is we're throwing some higher order terms away by writing that equation down. There has to be more going on than what we're talking about. But for the most part, if your delta t's are small and your delta l's are small, much smaller than your l's, say, and that's almost always the case, then this works really well. Because why? Because delta t is really small and alpha is pretty small. And if you square that thing, two small things multiplied together, it gets even smaller. And that thing that's in the negative sign there is really small, and you can kind of ignore it. So the question of what is L is not even there's no well-defined answer to what L is. You can use the beginning and it kind of works, but not quite. You can use the end and it kind of works, but not quite. As long as your delta t's are small enough and your delta l's are small enough compared to your l's, then it doesn't much matter what you choose. They both will work okay. That's the bottom line. But neither is technically right. Okay. Great. So what do I need to write here? Neither really work, meaning L is not equal to L initial or not final, but both are fine if delta t is small. And really, it's really that delta L is much less than L. Then you're in good shape using either one. Doesn't really matter what you choose because delta L is going to be small and your linear approximations are fine. Okay, next question. How are alpha and beta related? Let me go back up and show you these equations. Here, alpha, this is the definition of alpha and beta, the coefficients in this particular thing. So let's say I've got a substance, let's say copper, and I measure its alpha value, take a bunch of copper rods and I increase them in temperature by a certain amount and measure how much longer they've gotten. How will the beta value be related to that alpha value? They have to be related if you change the linear dimension of something, you have to think that the other dimensions are going to have to be changing in a similar manner. But how are they related? Any guesses? They are not the same. Good guess, though. Well, do you want to put some, and I just told you you're wrong, but it's not a bad guess. What do you want to share some thought process that went behind that? Yeah. Yeah, it makes sense. If you're going to change the length by something, you can change the volume as well. Close, but not quite. Any other guesses? It does not actually depend on the shape of the object. That's a good question. So if you had a cube of copper and you heated it, or a length or a rod of copper that with the same length as one of the sides would get bigger by exactly the same length as the rod gets bigger. So it doesn't actually depend on the shape. That's a good question, though. There should be a 3 involved somewhere, yeah? Multiplying or cubing, yeah, right. Probably a 3 involved somewhere, not a bad guess. The naive thing might be to say, let's just cube it, right? Shouldn't it be, well, L is V is length cubed. Shouldn't beta be alpha cubed? Why doesn't that work? Oh, well, okay. Well, shouldn't beta be alpha cubed? Did I say it backwards? V is L cubed. Shouldn't beta be alpha cubed? I don't know if I said that right, but that's what I meant to say.
Right. But then you would be cubing both, which would just make it way larger than it should be.
Make what way larger than it should be? The delta V? There's something very wrong with doing that. Very wrong. Anybody spot it? It screws the units up. Beta cannot be alpha cubed, because then it would have units of 1 over Kelvin's cubed. That's the tempting thing to want to do. You want to get beta from alpha, just cube it. That doesn't work because it doesn't even have the right units. So it has to be something more. There's something more to it, and perhaps there's a 3 involved. So let's. It turns out that we're gonna prove it here in a second. Turns out that beta is equal to 3 alpha. If you know one of them, if you know alpha multiplied by 3, you get beta. You know beta divided by 3, you get alpha. Why? How does that work? We can actually show that this is the truth. So let's consider a cube. That's y. Consider a cube. Break up my cube drawing skills again. Not bad, not bad. Okay, this cube is going to have volume V and the length L on every side. We know that volume is equal to L cubed. So let's heat our cube up. Heat it up. Heat it. So V plus delta V. Actually, I'm gonna move down here so I've got more room. V plus delta V. We know that that has to be L plus delta L quantity cubed. Each of those lengths is going to get larger by the same amount. And that new volume, V plus delta V, has got to be the cube of the new lengths. L plus delta L, del plus delta L, L plus delta L. Right? Sorry, I put it squared there. It should be cubed. Let's expand that out now. You actually get a lot of terms when you take this cube. This is equal to, we get an L cubed, which is nice, plus 3L squared delta L, plus L, sorry, there's a 3 here, 3L times delta L squared plus delta L cubed. That's V plus delta V. Okay, now here's what we're going to say. If L is much, much bigger than delta L, then some of these terms I probably don't have to worry about. They are so small as to be hopefully insignificant. But this is always what we're doing with any of these problems, really. We're taking an expansion of something and truncating the higher order terms because they're so small. So I'm going to say this term, obviously, we got to keep. That's a big one. If we throw away this term, then we're not going to have anything at all. Let's keep that one too. But this one has an L squared and a delta L in it. This one's got an L delta L squared and just one L in it. That's going to be way smaller than the second term. And the third one's even smaller. It's got a delta L cubed in it. So I'm going to say both of these things are going to be so small that I don't really have to worry about them. I can shove them under the rug and not even think about them. If that's the case, then we know that V plus delta V is about equal to L cubed plus 3L squared delta L. And we know that L squared is V over L. Let's plug that in for L squared and see what happens. This is about equal to, well, L squared is just, L cubed is just V. And this is 3 times V over L times delta L. And I've got a V plus delta V over here still. With me? I just threw out 2 terms and then substituted every time there was an L squared, L cubed on the right, I substituted in for a V. Except one time I had an L squared and I had to substitute in a V over L instead. Okay, subtract V from both sides. What happens? Boom, those terms go away. Now, where am I at? I'm at delta V approximately equal to 3V over L times delta L. Let's divide both sides by V. And I get delta V over V is about equal to 3 times delta L over L. And delta V over V well, let's write these equations down. Delta V equals V beta delta T, delta L equals L alpha delta T. Delta V over V is equal to beta delta T. And delta L over L is equal to alpha delta T. This is beta delta T, 3 alpha delta T. And the delta T's go away. And I get beta is about equal to 3 alpha. It comes from expanding that cube term and only keeping the first linear term in delta L. Okay, next question. So hopefully I've convinced you that this is going to come up a lot. I'm going to give you an alpha, you're going to need a beta. I'm going to give you a beta, you're going to need alpha. All you have to do is multiply by 3. And here's another hint. There's a question on a homework coming up that's going to ask you for the area expansion. Guess what the area expansion coefficient is compared to alpha? It's 2 times alpha. It's exactly that simple. For exactly the same reasons. You can go through the same logic. So, yep, yep. Right. So the question was, if you restricted it in 2 dimensions and didn't let it expand in those directions, would it expand 3 times further in this direction? The answer is yes, probably so. Or there would be some deformation where the pressure would be a lot higher if it couldn't actually expand in that direction. But yeah, if it is allowed to expand in that direction and can freely, the volumetric expansion must be there, and so it will expand 3 times further in that direction. That's right. So, okay. Here's another thing. This is, again, a complication that we're not really going to have to worry about, but I want you thinking about all of these actual physics things. Are alpha and beta constants for a material? I say alpha for steel is 0.003. Is that a constant at all temperatures? The answer is no. It's kind of a rhetorical question. The answer is no. Alpha and beta themselves often depend on the temperature of the thing that you're talking about. But again, over large ranges of temperature, that becomes important. Over small delta T's, it stays about the same, so you don't really have to worry about it. But if you're talking about really heating something from 100 Kelvin to 500 Kelvin, these equations are not adequate to do what you want to do. You're going to have to do, not only is alpha and beta, not only is, the approximation that we made, maybe you can't throw out some of those terms anymore, the linear approximation that we made no longer valid, but alpha and beta could themselves be changing as you go along. But it's a much more complicated process. We're not going to be thinking about any of those for this class, but I want you to be aware that those things are out there. Okay. Let's do an example. In the 7 minutes that I've got left, we've got 1 liter of water in a glass beaker at room temperature. Let's say room temperature is 20 degrees Celsius. And we heat it to 70 degrees Celsius. How much water is there now? Okay, so we need to know what beta is for water. And the beta at 50 degrees Celsius, which is about halfway in between, so it's not a bad value to use for water, is, I'll say B water, equals 4.57 times 10 to the negative 4 inverse kelvins. And also inverse degrees Celsius, because they're the same. Because this is a delta T. Again, we can go freely back and forth between kelvins and delta C here because we're talking about delta T. If we're talking about absolute temperatures, you cannot do that. Just to warn you. Okay, so let's plug it in. Delta V is beta times V times delta T. This is beta value is 4.57 times 10 to the negative 4 per Kelvin times 1 liter, which is our volume, times our delta T, which is 50 degrees Celsius, but it's also delta T of 50 Kelvin. Those are the same when you're talking about delta. Great, so the kelvins are going to cancel out. I can multiply these by these together. This is easy. Why am I even bothering to do an example with this? It's so simple. You just plug it in and get a number out for delta V. So you get a number that's 0.02285 liters. Great. So you had 1 liter of water to start with, and 50 Kelvin, 50 degrees Celsius later, you've got 1.02285 liters of water. What's the point of this silly example? It's about a 2% increase, a little more than 2% increase. But here's the tricky part about this problem. The glass expands too. So it's not going to read 1.02285 liters on the new beaker that you've got. Let's say there's markings on this beaker that let you measure the liquid inside there very accurately. If you heat up your beaker, it's no longer going to be reading the same 1 liter that's marked on the beaker is no longer being 1 liter. So the question is, really, what does it read on the new beaker when the beaker expands? That's the much harder question to answer. Let's try to answer that question. This is the true amount of volume that's there. This is not wrong, but it will not read this on the new beaker because the new beaker will no longer be reading in liters. It's going to be reading in something that is not liters. I'm about to figure out what that too is. So let's draw this again. Let's see. Do I have? I don't think I have a. I don't. That's okay. Let's go back here. Let's draw this thing. So here's my beaker. Let's make my beaker green. And here's my volume inside, and it said exactly 1 liter before. So I've got some volume, some hole, some cavity inside this glass container that's holding this water. Has that cavity gotten bigger or smaller in volume? It's not an obvious, the answer to this question is not obvious because the sides of the walls are both getting thicker. You could imagine that central cavity getting smaller. You could imagine that central cavity getting bigger if things are happening in the right way. Getting bigger because the bottom is expanding faster than this is happening. Is that going to be the same comment as up here? Let's think about the simpler problem before we tackle this volumetric thing. Let's imagine we have a steel bar and it's got a couple of holes in it. What happens to those steel holes? Does the area of those holes, and we're going to make this whole thing expand and get bigger by heating it up. Do the holes get bigger or smaller or stay the same? Would they get smaller? Would they get bigger? Let's do a thought experiment. Let's say this is a steel plate with those 2 holes in it, flat plate with 2 circular holes in it. And let's say we have the holes that we cut out of those circular plates, and they're over here. So we have those two circles of steel, when we heat it up, going to get bigger or smaller? They have to get bigger, right? Everything gets bigger. What if we took those holes and put them back into the steel plate? Would that work? You could imagine not even cutting them out. You could imagine just painting a little circle, and now you've got exactly the same situation. This is the thought experiment that should go through your head. The hole has to get bigger, because if you were to put steel in that hole, it would have to grow along with everything else. And it would be fine. You could imagine a third region that you didn't cut out that has exactly the same size steel circle in it. That steel circle has to get bigger. And so the regions around it also have to be getting bigger and expanding. So the answer is, any cavity within a substance will get bigger at exactly the same rate as the substance itself gets bigger. Okay, we'll finish this problem on Wednesday and think about what is actually, the reading on the beaker actually is, we'll come back to it on Wednesday. Okay, but now we have we know that our cavities are growing at the same rate as our substance. All right, see you Wednesday.